Welcome back. In this video, we are going to investigate another economic application of Karush-Kuhn-Tucker's theorem. Specifically, we'll be concerned with consumption, theory of consumption under budget constraints. So this is somewhat similar to what we did already, but our objective will now be very different. Okay, so one more example of Karush-Kuhn-Tucker. We'll tackle consumption under budget constraints. The setup is similar. Again, we have a number of products. We just number those 1 to n. We have prices for those products. Those will again be denoted by alpha 1 to alpha n, and we'll also use a price vector A. And we have a budget that is beta, a positive number. What we want to do this time is we want to determine the consumption level that is within budget and that maximizes a utility function. So in addition to the above, we have a utility function here that measures the utility that we get from a certain consumption. Specifically, we want our utility to be determined as a product of the consumption levels. So this is going to be a product of the xi, I from 1 to n. And we'll also introduce some constants, some exponential constants here, lambda i's, that can be used to express a preference for a certain product. So if one product gives you more utility than the other, then the lambda I for that product will be higher than for the other. Okay, so these will be constants. Lambda 1 to lambda n for a consumption of xi1 to xn units of goods 1 to n. Okay, so there's no desired consumption, but there's a utility function that we want to optimize. That leads to the following optimization problem. That is, then we want to maximize our utility. Subject to the budget constraint. The budget constraint is the prices times the consumption per product, all summed up, is less or equal to beta. And of course, we want our consumption to be non-negative. So the x's are constrained to be greater or equal to 0. And we'd all like to integrate this in one optimization model. To make things a little easier, we'll first simplify the objective function somewhat. And we'll do that by taking the logarithm. So if we take the logarithm of this function, remember, u was the product of the xi's to the power of lambda I. Then this is the same thing as taking the sum over the logarithms of the xi to the lambda I. Yeah, a logarithm of a product is the same as the sum of the logarithms of the factors. And as a second step, we can also take out the lambda I. That can be written before the logarithm. So that in that way here. Okay. So we can take this logarithm. The only prerequisite that we need here is the consumption of every good must be positive. We cannot take a logarithm of 0. But that seems reasonable because if there is a good that we do not consume at all, then the utility is always 0. There's a 0 in that product. So we wouldn't do that. Okay. Let's just make a quick note of that. So the prerequisite here is xi is greater than 0 for all I in 1 to n. Otherwise, the utility would of course be 0. So we'll just exclude that case from our optimization. Okay, and that makes the optimization a lot easier. Instead of a product, we now have a simple sum of factors. The logarithm is a monotone function. So if we maximize this new transformed utility here, then this will automatically also maximize the utility itself. Taking the logarithm doesn't change that. Okay, so we can now write down our optimization model in the desired form for KKT. So what do we have here? We have this objective function that we want to maximize. So we want to minimize its negative. We want to minimize minus the sum of the lambda I ln xi. We want to stay within budget. So that means subject to the sum of the alpha I xi minus beta is less or equal to 0. And we want all the x's to be non-negative, so we want the minus x's to be non-positive, like this. Yeah, let's all include this into the optimization model. Now, what happens if we do that? Well, this here is our objective function. So that means f of x is minus the sum of the lambda I ln xi. And you know, for KKT, we'll need the gradient of that function. So let's compute that right away. The derivative of the ln is 1 over xi. The lambda I just stays in place and the minus as well. So what we get here is for x1, for example, we get minus lambda 1 over x1, then minus lambda 2 over x2, and so on, down to minus lambda n over xn. So that's our gradient. We'll also have a look at the Hessian here, simply because it's that easy to get. You notice that each row of the gradient just contains one variable. So if you differentiate with respect to that variable, something will happen. If we differentiate with respect to a different variable, then the result will always be 0. So what that means is, for example, for the first row, differentiating with respect to x1 will give us lambda 1 over x1 squared, and the minus vanishes here. All the others will yield zeros. Yeah, for lambda 2, x2, just differentiating with respect to x2 will give you that term. All the others will be zeros, and so on up to lambda n over xn squared. Yeah, and again, all the rest will be zeros. So we get a diagonal matrix. And assuming the lambdas are positive, we can easily see that this matrix is positive definite. And we'll assume that from now on. So we'll assume lambda I are positive. Because what that means is that consuming a good actually increases utility. If consuming a good does not increase utility, then we wouldn't take that into account anyway. Okay, so that's an assumption that we can make. And what that means, the consequence of this is the Hessian is positive definite everywhere. So what we get from that is that f is actually a convex function. And that's important for the optimization part. Okay, as for g of x, the constraints, there's basically this one constraint about the budget, this one here. And then there is the many constraints on non-negativity or non-positivity, looking like this. We'll associate a multiplier with all of those because that's what we need for KKT later on. And we'll call those multipliers eta 0 for that budget constraint. And we'll use eta 1 to eta n for the non-negativity constraints. So those will be the multipliers we use. And as you know, we'll also want the Jacobian of g. And that can easily be computed. For the first row, we have a sum where all variables occur. Differentiating with respect to one of the xi's just yields that factor in front of the xi, so the alpha I. That means the first row just consists of alpha 1, alpha 2, and so on to alpha n. For the second row, we just have the variable x1 with a minus sign, so that will yield a -1 here and zeros everywhere else. And for all the others, it will pretty much be the same. We get a -1 for the variable itself, and we get zeros everywhere else. Okay? So that's how this Jacobian looks like. And finally, we can also state that g consists of linear or affine functions. So this is obviously also a convex function. So g is affine and therefore convex as well. So no problems here. Okay, so let's write down the KKT conditions here. KKT conditions. First one, gradient of f of x plus the Jacobian of g at x transpose times the multiplier y is 0. And by y, we mean this vector here. Okay, so in the long form, what that means is, remember the gradient of f that looks like this here. So we have these factors in the gradient. What we get here is these factors minus lambda 1 over x1 for the first row, for example, plus, and now we're transposing the Jacobian. So what that means is basically we're working along these columns here. We'll always have one of the alphas in there, and that will always be multiplied with eta 0, the first multiplier. And then there's mostly zeros with the only exception of this -1 that will be multiplied by the respective eta. Okay, so what we get here is in this case, plus alpha 1 eta 0 minus eta 1. That needs to be 0. And the same works for all the variables here. So we get this up to the point minus lambda n over xn plus, this is now the alpha n eta 0 minus eta n. Okay? So that same thing works. So that's the first condition. The second and third condition are easily checked. There is no third condition because we don't have equality constraints. The third condition just consists of the budget constraints. So sum of the alpha I xi is less or equal to beta, and the non-negativity constraints. The x are non-negative. The fourth condition is the condition on the multipliers, non-negativity of the y's or the etas. And finally, we also have condition number 5. Condition number 5 is the complementarity conditions, where we associate each multiplier with the corresponding constraint. So first complementarity condition says eta 0 times this constraint is 0. So what we get is eta 0 times that budget constraint alpha I xi minus beta is 0. And for all the other constraints, it simply says eta 1 times minus x1 is 0, times eta 2 times minus x2 is 0, and so on. And of course, the minus doesn't really play a role here. So what that means is we can simply say, well, the eta 1 times x1 needs to be 0, and so on. All these need to be 0. You already know that the x's can never be 0. We constrained our feasible set for that case, so we excluded that case because that would yield a utility of 0. So that means, as all the xi are positive, this condition simply translates into all the etas are 0, with the only possible exception of eta 0. Okay, so these don't really play a role. And that means we can even simplify all the other constraints a little. So in summary, what we have here are these constraints, where this last part here can simply be dropped, because those will be 0 anyway. So what we have is constraints of this form, lambda 1 over x1, minus lambda 1 over x1, plus alpha 1 eta 0 is 0, up to minus lambda n over xn plus alpha n eta 0 is 0. Then we have budget constraints. Sum over the alpha I xi is less or equal to beta, I from 1 to n. We have non-negativity on the x's, we have non-negativity on the y's, and we have this one complementarity condition here that remains, that says eta 0 times this budget constraint, that is 0. So basically what that says is, either we use our full budget, then this expression is 0, or if we don't use the full budget, then eta 0 has to be 0. That's the other possibility here. So one of these must happen. And let's mark this. And let's just have a look at those two cases here. So first possible case. What about the case where the alpha I xi is less than beta? So we don't use our full budget. Well, if that's the case, we know already that then eta 0 needs to be 0. But in that case, these equations here, those are greatly simplified to say, well, that means minus lambda 1 over x1 is 0 up to minus lambda n over xn is 0. And the lambdas are also positive, so that can never happen. Okay, so this is a contradiction. And that means the case cannot happen. We will always fully use our budget. So down to case 2. Well, what that means is, case 2, we use the full budget. So eta 0 may be whatever it is. Phi xi equals beta. So this complementarity constraint is automatically satisfied. Yeah, we don't have to care about this anymore. So we just have to see if we can find solutions for this. And this then turns into an equation. Okay, so doing so, from this first condition, what we get here is basically lambda 1 over x1 is equal to alpha I eta 0, and so on for all the lambdas and x's. So we can of course solve that for x, and we can get, well, x1 is then lambda 1 over alpha 1 eta 0. Same for all the others. Up to xn is lambda n over alpha n eta 0. Now, with this budget constraint at equality, we can simply use that, substitute our x's into that. And what we get is beta is equal to this sum over the alpha I xi. Now let's substitute our xi results in there. What we get is, well, there's 1 factor 1 over eta 0, that is in all of these. Then we multiply each of those with an alpha I, and that alpha I just cancels out. What remains are these lambdas. So what remains is just the sum of the lambda I. Okay, so if that is going to be beta, then we can solve. We can solve for eta 0. So then eta 0 is simply this sum over the lambda I from 1 to n, divided by beta. Beta is positive, the lambda I are also positive, so this is obviously greater or equal to 0. And that means this condition, y greater or equal to 0, that is fulfilled. And we can now use this eta 0 to solve for the x's. So if we do that, xj, let's call it xj, is of this form here, right? Lambda j over alpha j times eta 0. So if we just substitute that in there, what we get is lambda j over alpha j times 1 over beta, and then the sum of the lambda I. Okay, so in the end what we have is lambda j over the sum times beta over alpha j. And again, the lambdas are positive, beta is positive, the prices are also positive, or at least non-negative. Yeah, positive, they should be positive, otherwise I couldn't divide. So that is greater or equal to 0. And that means the condition x greater or equal to 0 is also fulfilled. So that is the solution that we get in the end. There's our multiplier. And there's our consumption levels. And what you can see basically is what happens here is the level of consumption on the one hand is determined by the budget and the prices. So this is kind of the cost of a good J relative to the budget that we have, because that will determine the consumption level. And the second is the relative utility it generates. So we have this fraction of lambda j that goes into that whole sum of the lambda j, of the lambda i's. Yeah, so this is kind of the relative utility. The other one is the relative price with respect to the budget. And those two factors influence your consumption decision. Now, it seems a reasonable outcome, I would say. And of course, that's always something that you should ask yourself. Does that outcome actually look reasonable? Especially in economic models. Is that something that we would expect? Or does that somehow seem strange? And now that you have that outcome, you can, of course, analyze what happens if you change any of the parameters. Yeah, for example, if you change the budget, then what happens is, well, consumption will increase in this model. And it will just increase linearly with the budget, basically. Same thing if you change the prices, then what happens is consumption of one of the goods will decrease, the one where you change the price. And if the utility levels of the lambda I changes, then again, the consumption will change linearly. So you can precisely tell what the influencing factors are and what they do, how they affect your consumption decision. And that's the value of these kinds of models here. Okay, so that analysis concludes our treatment of KKT, or our example of this application of KKT. Of course, there are a lot of economic models that work under similar conditions. So you have a function that is, in many cases, convex. It needs to be optimized, often a utility or a production function or something like that. And then you have constraints. And the way to solve these models is usually using KKT along the lines that we presented here. So that concludes this example. I'll thank you for your attention, and I'll see you in one of the next videos.